welcome to CEC lectures. Myself Dr. Preeti Jagmani from Department of Computer Science, Arabic College, University of Delhi. So in our previous lecture we have seen one of the memory management scheme, and that was segmentation, and why that memory management scheme was very useful, because there is a kind of we can say difference into there is a difference between what user perceives the physical memory as a unit and what actual the physical memory is. So users view of physical memory and the actual physical memory are two very kind of different, we can say, lookouts, or very different point of view. So in order to map this this view of user or the programmer to the actual physical memory, we need some kind of memory management scheme, which is segmentation. And today's topic is the another memory management scheme, which is about the paging. And we have let's say we also have when we try to look for these storage areas and so on and so forth, we also have some backing store which is having the same fragmentation problem as discussed in the connection of main memory. But here, as we are talking about the backing store, the access is much more slower than your random access memory, and because of this slow access problem, the compaction is also not possible, and the actual idea of your backing store is very different from what is being kind of perceived. So another memory management schemes comes into this scenario, which is named as paging. And paging is a very popular this memory management scheme. It is used in most of the operating system, which ranges from mainframes even onto our smartphones. So almost at almost in all kind of devices, this scheme of paging is being used. Now, how this paging is being implemented, that is taking some help or taking some cooperation from operating system as well as computer hardware both. So both of the components are involved here. Now let us see what actually paging is. So segmentation, we have seen that it is going to permit the physical address space of a process to be non-continuous. So it is not necessary for the actual memory to be continuous, because we have a kind of a savior management scheme in between, or a kind of mapping, which is segmentation. So similar is the paging, which is going to offer that same advantage, but yes, it is on the one side of the coin is it is going to offer the similar advantage. Another side of the coin is the two schemes are very different. How they are different, that I will be covering in this towards the end of this lecture. But let us first try to understand what is paging. So this paging actually avoids external fragmentation, and so is the need of compaction, whereas your segmentation does not provide kind of, we can say, safety against external fragmentation, while your paging is we can say paging is free from external fragmentation. Now all of the memory management scheme which came before the invention of paging, they suffer from one problem. What was the problem? The problem was fitting memory chunks of varying sizes onto the backing store. So we have various memory chunks whose size is obviously not unified, not common. So different size chunks, and all those chunks of data or are programs, whatever, are actually needed to be fitted onto the backing store. Now what was the problem with this? The problem with this is when a code fragment, or how this problem is we can say how this problem is taking place, what is being stopped by this particular problem. So when code fragments or the data residing inside the memory needs to be swapped out, and this process we also understand that there is a kind of swapping in and swapping out, that we have already seen in our previous lectures. We need to find a space on the backing store. Now that is one challenge, that the one space has to be found on the backing store. Another challenge is every time your system is looking for a different lot of space, different size of space, I can say. So this gives the idea of the paging paging as a memory management scheme. This paging involves breaking physical memory into some fixed size blocks, and these fixed size block of physical memory are called frames, while your logical memory is also kind of, we can say, perceived as the blocks of the same size, which are called pages. So logical memory, we can say, is actually breaked into blocks of some size, which are pages, and that particular similar size physical memory is also breaked into those physical size block, fixed size block, and those are called frames. So for physical memory it is frames, and for logical memory it is pages. And what is happening when a process is to be executed? This process is to be loaded into any available memory frame from their source, which could be a file system, which could be a backing store, or which could be any other kind of storage area. When this process has to be executed, the pages are loaded into any available memory frame, and these are taken from their source. Now that backing store is divided into fixed size block, and the size of those blocks is actually equal to the size of the memory frames, we can say. So here we have frames, and here we have pages. And now if you can kind of imagine, let's see that these pages, the content of the pages and the frames are being swapped in and swapped out depending upon which particular process is being accessed currently. Now what are the consequences, or what are the, we can say, advantages, whatever, of this particular scheme? The logical address space is now totally separate from your physical address space or from physical memory. So a process can have a logical 64-bit address, which is going to generate which is actually a big address, I can say. Even your system is having less than 264 bytes of the physical memory. So even your physical memory is very, very small. Here on the other side of the we can say application, which is dealing with the logical addresses, these logical addresses can be kind of very, very big, because ultimately these logical addresses are going to be converted into whatever is permissible within the physical memory. And this process we have also seen in the segmentation. Here we are dealing with one side, it is the backing store, and another side it is actually the physical memory. Now it is CPU who is going to generate the addresses. So the address generated by the CPU is divided into two parts, a page number and a page offset. So please recall, earlier we were having the address of this logical address space into segment number and the offset, segment offset. Obviously here we have a page number and the page offset. So page number is used as an index to the page table. Earlier we have the segment number was used as an index to the segment table. The page table contains the base address of each page in physical memory. And what this page table is having? This page table is having base address of each page in the physical memory. Now this base address is combined with the page offset to define the physical memory address that is sent to the memory unit. So the process, if you can kind of compare the two processes of segmentation as well as of paging, you will find many similarities between the two processes. There it was a segment table, here it is a page table, page number and offset, there it was segment number and offset. And here also the base address is combined with the page offset in order to define the physical memory address, and that physical memory address after being generated is sent to the memory unit. Now let us take a look at the kind of this paging mechanism with the help of a figure. So here we have one logical address which is having two we can say two items into it. One is the page offset and one is the page base page address we can say, and another one is the D, which is the offset. Now here we have page table, so that P, which is the index of that particular page into the page table, is being referred to. If you can see with the help of an arrow, this is being a page table is being contacted, a page table is being concerned, and then whatever frame address is being, now these frames are of actual physical memory. Whatever frame address is being written in front of that index P in the page table, that frame number is being retrieved, and again it is combined with the offset D, and finally we have a complete kind of frame along with an offset. That means how much is to be shifted into a particular frame if it or within the cluster of the frames. So here let us try to kind of see it once again. The CPU is going to generate a logical address consisting of two parts. One is P, another one is D. D is kept as it is. P is being checked into the page table. Whatever corresponding frame number is there, that frame number is being taken. That frame number is being combined with D, and finally we are going to generate one complete physical memory address which is referring to some frames, because here those blocks are named as frames, while in the logical address space those blocks are named as pages. So here if you can see, we have 4 pages in the logical memory, which is page 0, page 1, page 2 and page 3, and here we have a page table which is showing us what is the frame number corresponding to that particular page. So if we can see, corresponding to the page number 0 we have frame number 1, corresponding to page number 1 we have frame number 4. Similarly, corresponding to page number 2 we have frame number 3, and corresponding to page number 3 we have frame number 7. And here inside the physical memory you can see that the page 0 is stored inside frame number 1, the page 4 is the frame 4 is being given to page number 1, the frame 3 is being given to page number 2, and the page number 3 is being resided inside the frame number 7 as the page table is saying. So this kind of memory, this kind of mapping actually is happening within the logical memory as well as the physical memory, and we can say the best part here is the equal size of the pages as well as the frames. So it is going to kind of it is going to save some kind of we can say fragmentation. Which kind of fragmentation, that we will be seeing in a short while. So we have the page size. Now the question comes up, how we are going to define this page size. As we have defined the frame size with the help of the hardware, similarly the page size is also being defined by the hardware, and it is going to be equals to the frame size. Now the size of the page is a power of 2 that we need to make sure of. Now this power of 2 is varying such that the size will depends the size will vary, or the numbering will vary from 512 bytes to 1 GB per page, and that depends on the computer architecture. We can also deal with the clusters of the frames. We will be seeing it in a while. The selection of power of 2 as a page size make the translation of logical address into a page number and the page offset particularly easy, because we are actually dealing with the physical addresses which are hexadecimal numbers we can say, and are the number system also here is the binary. So, the size of the page is the power of 2. Size of the page will vary from 512 bytes to 1 GB. Now, what will be the actual size? That depends on the computer architecture, how how long or how large page can be handled by that particular computer. And selection of power of 2, as we know in computer science, is going to give us an kind of an easy calculation way. Now, let us try to understand that. Let us say if the size of the logical address space is 2m and the size of the page size is, let us say, 2n bytes, or one is m and another one is n, then the higher order m minus n bits of a logical address designate the page number, and the n lower order bits designate the page offset, and the total logical address will be kind of seen as you can see on the screen. We have two parts of logical address. One is the page number, another one is the page offset, where page number p is is residing inside m minus n numbers, m minus n higher order bits, while the low order n bits are designated for page offset. Here let us recall that P is an index into the page table, where D is the displacement or offset within that particular page, and the total the size of this logical address is obviously m, we can say m bytes. Yeah, so m bytes. So m minus n is designated for page number, and the last n are designated for the offset. Now, how it is going to take place? So, here inside the logical memory you have pages 0, 1, 2, 3 starting from 0 till 15. So, total 16 pages, and different we can say these what you call the contents in the form of ABCD, or pages in the form of ABCD is being shown. Then there is a page table which is having four entries of page numbers, that is page number 0, page number 1, page number 2 and page number 3. These 0, 1, 2, 3 are separated in the logical memory. The first chunk itself is of the page number 0, the second chunk belongs to the page number 1, and so on and so forth. And here we have the corresponding mappings of the frames. So, corresponding to 0 we have frame number 5, corresponding to 1 we have page frame number 6, corresponding to 2 we have different frames, and then so on and so forth. So, here if you can see in the physical memory, here we have given a paging example for a 32 byte memory with 4 byte pages. So, every page is of 4 byte, as you can see inside the logical memory, or you can see inside the physical memory. So, these 4 bytes are, let us say, A, B, C, D, that is going to make one page. And here we also we will be calculating offset also, but this example is representing a 32 byte memory. Now, why 32 byte memory? Because here we have 8 chunks, we can say. So, 32 is actually here that comes into figure by 8, and we have each and every page of 4 bytes. So, this kind of mapping is there, and whatever page table, whatever mapping is being generated by page table, that particular page is going to be resided inside the physical memory into that frame. So, as you can see, the page number 0, the frame number has been designated as 5. So, the 0, 1, 2, 3, 4 has been shown blank, and then from 4, 0, 1, 2, 3 has been shown blank, and from 4, if you can see, whatever the contents of page chunk 0 are there, those are stored here in starting from 4, 5, 6, 7, because each and every page is a 4 byte, we can say, page, or each and every frame is a 4 byte frame, and the total memory is of 32 bytes here. Now, here we have seen The logical address is having n is equals to 2 and m is equals to 4, and we have also seen the example of this m and n in our earlier figure. So, we are going to use a page size of 4 bytes and a physical memory of 32 byte, which is 8 pages that we have seen. Logical address 0 is actually page 0 offset 0 because there is no shift there. Indexing into the page table, we discovered that page 0 is in the frame 5 as we have seen. Thus, the logical address, how this mapping is being happened is logical address which is logical address 0 is going to be mapped to the physical address 20 because 5 multiplied by 4 is equals to 20. So, if we can see another example, we have a logical address, let us say 3. So, page 0 offset 3 is going to map to the physical address 5 multiplied by 4 plus 3. Logical address 4 is page 1 offset 0, let us say. So, according to the page table, page 1 is mapped into the frame 6, and here we have similar mappings where logical address 4 maps to the physical address 24, which is 6 into 4, and logical address 13 maps to physical address 9, and so on and so forth. Now, with this scheme we have seen what is paging actually and the segmentation that we have seen in our earlier lecture. Now, both are memory management schemes, both are having kind of some support of some hardware which is going to provide a kind of mapping to these schemes. Segmentation is maintaining a segment table, paging is maintaining a page table, but there are still with all these commonalities various we can say differences are there between paging and segmentation. Let us try to explore these differences. So, in paging, a program is divided into fixed or mount size pages. So, we have seen 4 byte pages in our earlier example, while in segmentation the program is divided into variable size sections. So, one section is of let us say data, another section is of procedures, third section is of let us say stack. So, all these are variable size chunks we can say. And for paging, your operating system is accountable, while for the segmentation your compiler is accountable. Why? Because kind of we can say parsing or separation of these elements of the program is the job of the compiler. So, segmentation is for segmentation our compiler is held accountable, but for your paging your operating system is accountable, or it goes with the help of operating system. Then we have what will be the size of page or what will be the size of the frame. So, the page size is determined by the hardware, while here section size can be given by the user because different sections are there and all the sections are having different data or different programs to be stored and different varying sizes also. Now, paging, because of this kind of similar same size advantage, it is faster as compared to the segmentation, while segmentation is a little slower as when compared with paging. Now, one very important thing, paging is not going to result into the external fragmentation, but it can result in the internal fragmentation because the size of the page or the frame is fixed, while the segmentation is having different segments of varying sizes. So, segmentation could result in the external fragmentation, and while paging can result in the could result in the internal fragmentation. In paging, we have seen that there is a logical address which is being split into a page number and an offset, while in the segmentation we have seen that the logical address is split into the section number and the section offset. Then we have paging. When we talk about how it is going to be kind of implemented. So, paging comprises a page table that encloses the base address of every page, while here on the side of the segmentation we have a segment table which encodes a segment number and the segment offset. Then the page table is employed to keep up the page data. Section table maintains the section data. That's very obvious. Then we have in paging, who is going to maintain that free frame list? It is the operating system which is going to maintain the list of what is free in the actual memory, while in the segmentation this is not being maintained in the form of a frame list, it is maintained as a list of holes, because here there we do not have any kind of, we can say, fixed size frames or pages. Now, a paging is a technique which is kind of invisible to the user, while segmentation a user can see or user can control, we can say. In paging, the processor needs the page number and an offset to calculate the absolute address, while in the segmentation the processor uses the segment number and the offset to calculate the full address. Now, apart from that, if we go into kind of hardware details, or if we go into the protection mechanism about these two memory management scheme, we will come to know that it is very difficult to allow sharing of procedures between the processes when we talk about paging, while the sharing of procedures between the process is very easy as your segmentation is, as far as your segmentation is considered, and these details come from actual kind of hardware implementation or actual protection mechanism which is being employed for various processes when paging is done or when segmentation is done. So, we can say it is difficult to allow sharing of procedures between the processes when a paging is being performed, while in case of a segmentation sharing of procedures is an easier task. Then we can say in paging a programmer is not able to efficiently handle the data structures, while your segmentation is totally about the different data structures being stored differently or separately, we can say, then one chunk of the program is stored separately. So, it can efficiently handle data structure. The protection mechanism is hard to apply when we talk about paging, and it is easy to apply the protection mechanism in case of the segmentation. Then the size of the page needs always to be equals to the size of the frame. That is the first thing that we have already seen, and then there is no such constraints on the size of the segment, as they can be different. A page is referred to a physical unit of information, while segment is more referred or more kind of concerned as the taken as the logical unit of the information. Paging results in a less efficient system as far as user's point of view is concerned, while the segmentation refers in a more efficient system. So, here in this lecture we have seen what is actually paging, how it is kind of, we can say, taking place, what kind of mechanism is required. And with the previous scheme of memory management scheme segmentation, here we have also seen what is the difference between the paging and the segmentation processes. Here is a list of references which is being used for preparation of this lecture. Hope you have enjoyed the lecture. I will see you in the next one. Till then, take care. Goodbye.